All right, we're going to work some shear and moment diagrams today. And we've got about 10 problems, and we're just going to work through these organically. So here we are with problem one. And in this beam, we already have the reactions given to us, right? We're just given a free body, so we don't really know what the context is. But we're going to do something like this. To our shear diagram and our moment diagram. And for our shear diagram, start at 0, follow the direction of the arrow. Nothing happens. Follow the direction of the arrow. Nothing happens. And follow the direction of the arrow to get back to 0. Okay, so there is our finished shear diagram. It looks like that. And you do need to include units on these. So the easiest way is just to come over here and do it in the legend, right? So we're going to do this in kips. Okay. Everyone knows the sign convention. So up, down, positive shear force here, down, up, negative shear force plots down there. All right. Let's do a few shear diagrams, and then we'll come back and do moments in a minute. So here we have another beam, and we're going to go through the same type of process. So I like to do my vertical lines first, do a line for shear and a line for moment. And yeah, so start at 0, increase up to 20. Nothing happens. Decrease by 20. Nothing happens. Decrease by 20. Nothing happens. And increase by 20 to get back to 0. All right, so there is our shear diagram. We're going to want to label these points. This one I'm just going to go ahead and label as 0. Be okay, I think, to leave that off as well. And put the units over here in the legend. Okay, let's do another shear diagram. All right, so we'll do these vertical lines. V, M, and units while we're here, kips. Switch over and do our diagram. All right, so we're going to start at 0, end at 0. First, we have 20 kips, an abrupt change in shear up, so we jump up to 20. Then over the length of the beam, we decrease by the area of this curve. So 2 kips per foot times 20 feet is 40 kips. So positive 20 minus 40, that lands me at negative 20. By the way, it's my habit not to put a negative sign here, right? Because the picture shows that it's negative. But I know that some people and some professors like a negative sign there. So if you want to do that, I'm not opposed. Just not something that I typically do. And if we're integrating a constant load, my shear function is linear. So we're going to have this type of shear. Okay, on to the next one. This one's a little more involved, but that's okay. Okay, and we're doing kilonewtons in this one, switching over to SI system. All right, start at 0, increase by 11. Over the next 4 meters, we decrease by the area under the curve. 3 times 4 is 12. 11 less 12 lands me at -1. How do I get there? Constant integrates to linear. A moment does not affect the shear diagram. It only affects the moment diagram. So we ignore it. 9 kilonewtons down, -1 minus 9 lands me right about there. -10. I do make an effort to draw to scale-ish. Okay, so as you can see, I'm not working from graph paper, but I'm still mindful that one should look about 1/10 of 10, ballpark kind of assessment as I go. All right, nothing happens here, and increase by 10 to get back to 0. You will always, always end and begin at 0 in these problems. That is because we are executing an equation of equilibrium piecemeal. All right, let's come back to this one in a minute. This one has some supports there. So let's go back to this first example and let's start to work on our moment diagrams. So our moment diagrams are the integral of shear. So we're doing an integration step to go from shear to moment. And that means we're taking the area under the shear diagram. And if I were to look at, let's say, the dimensions for this block here, so the height is 20 kips. The length or width is 10 feet. So this area is going to have units of kips times feet, and that is going to be what we label in our bending moment diagram. Sign convention, right? We're going to do kind of smiles on top, frowns on bottom. So we know our positive bending moment looks like this, and our negative bending moment looks like that. Okay, at this point, we're doing areas under the curve. So start at 0, end at 0, 100% of the time. Positive area values increase. Negative area values decrease. I think I'm going to do moments in purple today. Okay. Constant goes to linear. Constant goes to linear. And that is it for my first moment diagram. I do need to compute and label that top component. So the area under the curve up here is 20 times 10, 200 kips times feet. That is my maximum moment. All right, on to number 2. So my moment, so I'm going to be multiplying units of kilonewtons times meters. So kilonewtons times meters are my units here. Start at 0, end at 0. We all know the sign convention. All right, our first block has an area of 20 times 4. It's positive area, so we increase. I'm going to draw that a little bit smaller just because I know I want to make room for that shear diagram. Okay, so I increased by 20 times 4, area under the curve. That gets us up to 80 kilonewtons times meters. How do I get there? Constant integrates to linear. For the middle segment, the 4-meter segment, I have 0 shear force. Integration of a function equal to 0 gives me a constant function. So there is no change in bending moment in the intermediate 4 meters of this beam. So constant function, so that's still at 80 right there. My line doesn't look perfectly horizontal, so use your imagination a bit. And finally, we have a negative area. 20 times 4 is 80. This time it's negative, so we decrease. That gets us back to 0. And that is our moment diagram. All right, go on to number 3. Check our units. We're going to do kips. Sorry about that. Kips times feet. So kip feet or foot kips. Start at 0. We have a positive area, so we increase to a local max. How do I know it's a local max? If shear has a value of 0, moment has a local min or max because shear is the derivative of moment. And then I get to decrease, so I got a negative area there, so that'll get me back to 0. Let's compute and label this peak moment. It's the area under the curve. So I've got my 20, using that calculator on the left. So I've got my 20 kips times 10 feet divided by 2 because it is a triangle. And that gets me up to 100 kips times feet up here. All right, now we need to decide how we're going to get there. And this is where errors are often made as people learn how to do this for the first time. So linear integrates to quadratic, but the question is it a concave up quadratic function or is it a concave down quadratic function? Okay, so this is where most of their errors are. Same thing on the other side. Is it a concave up function or is it a concave down function? All right, so let's think about this for a minute. The way that I prefer to teach this is as follows. If these values are decreasing from left to right, then the moment is concave down. Okay, so there's a good kind of trick that works 100% of the time when you're going from shear to moment. Are the values increasing or decreasing? Another way to think about it is to think of the slopes. So I'm going to switch colors to orange. So we know that this value is a positive slope. We know that this 0 is a slope of 0. And if I were to grab an intermediate one, it's still positive, but not as steep as the orange, or something like this. Okay, so that's another way to reason through these. In order to do it nice and quickly, my little trick will also work for you. So values decrease from left to right, therefore concave down. And as you're learning, right, I would spot check the slopes as you go. So again, I'd come over here and be like, okay, I've got a negative value. Do I have a negative slope? Yes. Okay. And do I have a steep slope here compared to a less steep slope here? Absolutely. Okay. So there's little calculus checks that you can do along the way to make sure that your answers make sense. Okay, on to the next one. Just occurred to me, I probably should number these as I go. So I've got number 1, number 2, number 3, number 4, and number 5. I'll try to remember to update these as we go. All right, so number 4, yeah, we already did the shear diagram. Sorry. I forgot that we had done that. Okay, so number 4, I've got a beam. I've already done my shear diagram, and now it's time to work on my moment diagram. And I know I need these areas under the curve. And so the first challenge to this one is that I need a new line. I need a new line, and my new line is going to go like this. So what I want to do is capture where my shear force is 0, because I need to take this area and make a positive increase in moment. I need to take this negative area and decrease my moment. All right, so in order to do that, I need to determine what is this dimension from here to here. I'm just going to call that arbitrarily x1. And what is this dimension, which I'm going to arbitrarily call x2. And I always see students working too hard to figure out what these are. Okay, the best and fastest way to do this is to remember that to get to the free body, to our shear diagram, we integrated with respect to the x direction. Okay, so what does that mean? It means that the slope of the shear diagram, is equal to the value of the loading diagram. So if we were to generically call this W, okay? And if I were to call this plot here generically V sub 1, the shear coordinate at some at some point in my plot, then what I can say is that V sub 1 is equal to, no, X sub 1 is equal to V sub 1 divided by W. All right, let me make sure that's clear what that comes from, okay? So here we have a constant W, 3 kilonewtons per meter. Here we have a rise and run relationship in my shear. My rise is V1, my run is X1. So I would say the slope of the shear diagram right there is equal to the rise, V1 minus 0, over the run, X1 minus 0. And I also know that the slope of the shear diagram is the derivative of the shear diagram with respect to X. And by definition, that gets me back to my loading diagram. So I'm going to plug in W here and rearrange to get that. Okay, so take a look at those steps. Plug in W for slope, rearrange. This is a good little equation, relationship, whatever you want to call it, to keep in your back pocket. As we apply that to our problem, here's how this simplifies. All I need to do to figure out my X1 is I say 11 divided by 3. So X1 is 11 over 3 meters. Okay, we can do the same thing for X2. So now we're looking at this little tiny triangle, and it has a rise of 1 and a run of X2 and the same W, 3 kilonewtons per meter. So my X2 is simply 1 divided by 3 meters. Okay, apologies for the break. Let us continue. The rest of our areas are pretty straightforward, and I have a habit of just kind of doing little side calcs for these. So I'm going to do that in pink here, right? So this area has a base of 11/3, a height of 11, and it has the area of a triangle, so divide that by 2. Okay, this little negative triangle here has a magnitude of a base of 1/3, a height of 1, it's a triangle divided by 2. This piece here has a rectangle that is a 1/4. So that one is 4 kilonewtons times meters. These are all magnitudes, right? I don't put any plus or minus signs with my areas. And then the last one is 10 times 4, which is 40. All right, I think we've got some good information. So we are good to start our moment diagram. So again, we start at 0, we end at 0. We need units. For this problem, it's kilonewtons times meters. force times distance for moment. I start at 0, and as soon as I start to get these fractions involved, I just use my calculator. And that way it's keeping all the sig figs as I work through the problem. So I've got 11 times 11 divided by 6 as my first piece. Okay, so that puts me up here. So increasing because the area is positive, and I label that 20.16 bar. Now I want to decrease by the area of this triangle. So go back to my calculator and I hit minus 1 divided by 6, enter. Okay, and so that lands me nice at 20 here. Now I decrease by 4, which gets me to 16. Oops, I forgot something important. Okay, so I'm gonna add 4 to get back to my 20. Okay, so I'm here at 20, and this, what I almost forgot, I don't want you to ever forget, which is when you have an applied moment or a reacting moment, that needs to go into your moment diagram as a jump at a discontinuity. Sign convention always feels frustrating when students first learn it. And I always teach it as saying just brute force memorize for now. The reason why this works will become clear later. But clockwise means jump up. Counterclockwise means jump down. For ours, we have a clockwise moment, meaning that we jump up from 20 plus 24 to get up to 44. And I didn't quite plan this as well as I would have liked. I'm a little light on room, but that's okay. We're gonna go with the flow. All right, now we're up at 44. Now we reduce by 4, minus 4 equals, and that gets me down to 40. Trying to draw this sort of kind of roughly to scale here, even though I'm writing right on top of my shear diagram in this example. Sorry about that. And then lastly, decrease by 40 to get back to 0. Okay, so I get back to 0 there. All right, so, things of this magnitude of complexity and above, I always use my calculator as a tool, especially when I have these decimals. What you're going to find out in shear moment diagrams is that if you round prematurely, you won't be able to get back to 0. And then you've got to analyze whether you just have a rounding error or a concept error. So I'm in the habit of keeping all of my decimals in my calculator as I work through the problem. All right, let us draw these curves. Let's do the easy ones first. So constant goes to linear. Constant goes to linear. It didn't look very linear. Linear. Okay, that was better. That jump we did was from 20 up to 44, that vertical jump. So I'm going to put that there. And so I'm going to emphasize, I'm going to just kind of trace over these so they're a little easier to see. And I'm going to color code as we go so it's clear where we are in this process. Okay, so we've got the right side of this thing licked. The only thing we need to add in is we've got a linear function there. We know that integrates to quadratic. So the question is it concave up or is it concave down? And we determine that by looking at these values. They decrease from left to right. Therefore, the moment diagram is concave down. And it should be a nice smooth parabola to connect those 3 points. Right. That one is done. Let's go on to the next problem. So number 5, here we've got to do some reactions. And we're going to need to release the body from the supports, get some reactions in there. and do a little bit of simplification. So let's have some fun with this one. The first thing I'm going to do is remove this roller support. I'm going to remove the roller support and just kind of take out the PIN right there. And on the other side, I'm going to remove the support. Okay, and when I remove the pin, I usually kind of color white over there to show that there's a hole in the beam now. Kind of a lot of detailed information for shear moment diagrams, but a good reminder all the same. Okay, so our roller, we can only do a vertical, and the pin, we could do a vertical and a horizontal, but there's no net horizontal force in the system. So I know that one's going to be 0. So I'm going to assume this one is upward. I'm going to assume this one is upward. I'm going to call these A sub y, B sub y, and let's go ahead and solve those very quickly. We're going to be able to do a little bit of simplification here. So I'm going to take these two kip forces at a distance of 4 feet and turn those into 2 times 4 equals 8 kip foot of moment right there. So using some of those static equivalency relationships. And once I do that, I don't need to mess with these anymore. I can just leave that as a moment, get some of this extra information out of the picture. Okay, I could also do area under the curve for this little distributed load over here. So I know that that resultant force is 2 times 5 is 10. So I'm thinking of a resultant force of 10 kips here. Now, be careful, all right? You can do static equivalency for reactions all day long, and it's okay. You cannot carry that forward into shear moment diagrams. You will get an error. Okay, so we can change that to 10 kips for the purpose of getting reactions. And then after that, we're back to the 2 kips per foot. I want to make sure that's super clear. All right, let's set up this equation. So I'm going to let's do a moment summation. Summation of moments about A is equal to 0. And how many terms am I going to have? 1, 2, 3, 4, 5, and set those equal to 0. So first term, 5 at a I should use units because I'm teaching. Hang on. That was a sneeze. All right, 5 kips times 2.5 feet. Sign is negative. Next term, 8 kips times foot. Sign is negative. Next term, 25 kips times 10 feet. That one is positive. Next term, 10 kips times a distance of 5, 10, 15, 17.5 feet. That one is negative. Under the assumption that by is upward, my last term is b sub y times 5 times 4, 20 feet. And that one is positive, and that is set equal to 0. All right, so calculator, minus 5 times 2.5 equals minus 8 equals plus 25 times 10. Okay, equals minus 10 times 17.5 equals, and then I do times -1 to move it to the right side of the equation, and then divided by 20 to get this answer. Okay, And this is the point where we need to remember the sign convention that a negative sign here negates or reverses our assumption. So the best way to communicate this is just rewriting it 2.725 kips down and kind of call that a final answer. All right. Let's solve for a sub y by doing a force summation. Summation of forces in the y direction equals 0. Upward is positive. All right, so again, we're assuming a sub y is positive upwards. So that's our first term, a sub y. Minus 5. Moments don't go in a force summation. Plus 25. Okay, minus 10. And then we have plus b sub y, in which b sub y is opposite that. So I'll keep the negative 2.725 kips and set that equal to 0. I still have this in my calculator. Okay, so let's just take that and then minus 10 plus 25 minus 5, and then times negative 1 to put that on the right side of the equal sign. So we have a sub y is equal to negative 7.275 kips upward. So 7.275 kips downward is where and how it actually acts. Now in shear moment diagrams, you're gonna want to keep the sig figs. You're going to want to keep the sig figs. So it's kind of the exception to the rule, when in most of our problems, we can kind of lop off anything past the fourth sig fig. Now our answers here are precise to excuse me, to 4 sig figs, right? So it's not quite applicable here, but in general, store that number, keep it in your calculator, keep it in your spreadsheet. Don't lop it off because you'll have a rounding error at the end that then you'll have to deal with. All right, let's go ahead and as we move from reaction mode to shear and moment diagram mode, I'm just going to clean this up a little bit. It's going to be harder said than done, isn't it? Okay. All right. So we will color over the support again. Okay, close enough. And over here at A, we determined that A sub y was a downward reaction and equal to 7.275 kips downward. And at B, we have 2.725 kips downward. All right. I no longer need these reactions, so I'm just going to remove them from my document. I also no longer need that 10 kip force. So I'm going to remove that from the document as well. And we are good to go with shear and moment diagrams. I'll go ahead and zoom out. Let's get these lines going. There we go. I need one there. And I need one here. Okay, so here's going to be my shear diagram. And here's going to be my moment. And let's go ahead and do units. So my shear will be in kips. My moment will be in kips times feet. And goodness, I think we are ready to follow the rules. So let's see, I'm doing blue for shear diagrams today. Start at 0, immediately decrease. Immediately decrease. And I've got that number in my calculator, so I'm just going to leave it there. And nothing happens for this first little piece. Then we decrease by 5, so -5. And as you can see how I'm keeping that fifth sig fig for accuracy? That's important. Okay, nothing happens between here and here. The moment will cause a jump in my moment diagram, but it does not affect the shear. So I just continue on my way. I get to 25, add that in my calculator. That puts me up at positive 12.725, somewhere up here. Let's see, nothing happens here till I get to there. And now I decrease by that 10. So subtract out 10. That lands me at positive 2.725. How do I get there? Constant integrates to linear. There's my nice linear function. And now final vector, decrease. And man, it is satisfying to do this last term, 2.725, and get to 0.0000 on your calculator. Okay. If you do any rounding out along the way, you won't get back to 0. And then again, you're like, okay, is it a precision error or is it an actual concept error that I need to fix? All right, my shear diagram's looking good. And we are ready to do the moment diagram. I'm going to clear out my calculator. And I'm going to do purple. And I'm going to try not to forget to jump here. Why don't I just like draw a line? That's not a good color line. How about this one? All right, I'm going to draw like a purple line there. That's going to be my way that I'm going to remember to go back and do this discontinuity. Procedure is the same. Start at 0, end at 0. My first area is negative. So on my calculator, 7.275 times 2.5, just times -1. Want it to be a negative number. All right, so we're off to the races and we're already down at 18 point. Now, for the purpose, as long as you're carrying the digits in your calculator, by the way, I'm fine with you rounding what you write on your paper. Does that make sense? Okay, so we'll go ahead and just show the 3 sig figs there. That is okay. And then continue on our way. So we've got our next area. And so it is, so I want to minus sign. Okay, so I want to subtract that. And let's see, the height is 12.275 kips times 2.5 feet. Okay, so that takes me down to negative 48.875. You know what, I'm going to round this 48.9 there. Okay, all right. Now I want to jump by a small amount, only 8 kip feet. But do I want to put a positive or negative term? And I remember that a clockwise means jump up. A clockwise moment means jump up. So I want to add 8. So now I am at 40.9, roughly. All right, now I have a big area, so I'm going to decrease by, so minus. So I've got 12.275 times 5. Okay, ooh, I'm going to run out of space on my paper. Okay, luckily we're about to get some positive stuff going on. So this isn't going to be quite to scale. I'm going to draw it about as low as I can, and we're going to make that 102.3 is sufficient for that. Okay, let's do this positive area. So finally a plus sign. 12.725 times 5. Okay, that gets me up to negative 38. So somewhere around here. And now we need to increase by the area of a trapezoid. So we're going to do a plus sign. And I'm going to take the average height multiplied by the width. Okay, so I'm going to take 5, that's the width, times open parentheses. And so I want to say 12.725 plus 2.725, close parentheses, divide by 2. All right, close up that term. And this is when you cross your fingers and hope that you get back to 0, right? And sure enough, 0E0, what a happy number in my calculator. I will say when you're learning this, you're often not going to end at 0 and have a mistake to go find. So when you get frustrated, just recognize that it is a very normal part of learning how to do this particular type of operation. All right, let's do our functions. So constant, most of it's constant, all that integrates to linear. So just like in kindergarten, we're going to connect the dots, connect the dots, connect the dots. All right, for the last portion of the curve, we have a linear function. So that's going to integrate to quadratic, values decrease, therefore concave down. And so a nice smooth function like this. And if you want to draw these really precisely, the slope needs to be coming off at a tangent to that former function. That's not a bad one right there for a hand drawing. Okay, let's go ahead and get this thing colored in, and that one looks good to go. Boop, 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 boop. Okay. Now, one little thing that I want to add in is when you are being tested on this kind of thing, okay? So you wouldn't do this in the workplace, but for your professors, we want to make sure that you know what function that is. So for these higher order functions, you could just label them as quadratic, cubic, quartic, whatever they are. And then the rest, we can assume linear by default, but, feel free to label a little bit, just in case things are not clear. So if we wanted to do that for consistency, these higher order functions, I'd prefer to have these labeled as quadratic, quadratic. Abbreviations are fine. That one doesn't have any. This one doesn't have any, that kind of thing. Okay, let's go on to the next problem. So here we have, goodness, a much simpler one. All right, let's enjoy a simpler problem. So I've got a little cantilever beam, and I do need to get the reactions. And after I get the reactions, I'll be doing my shear and moment diagrams, units of kilonewtons and kilonewtons times meters. Picking out my blue. Oh, let's do the free body first. All right, we've got to free the body from the support. So we're going to take off the fixed connection from B. And we know a fixed connection can generate force reactions and moment reactions. And in a 2D problem like this, it would be moment reaction. So we need the sum of forces to be equal to 0. So 4 kilonewtons up achieves that purpose. We also need our moment reaction. So some moments about A, some moments about B. Put the thing in static equilibrium. We're going to get 8 kilonewtons times meters here as a reaction. If you're having any trouble at all getting these very quickly, please reach out and get a little bit of help. All right, now that we have our reactions, we are ready for our shear diagram. So I start at 0 and nothing happens. There is no shear over that first 1 meter. And that makes sense if I were to come in and make a cut through the beam right there. Clearly, there's no shear force there. It's completely unloaded. But once I get to the 4 kilonewtons, I follow the direction of the arrow down. and then nothing happens. Okay, and then increase by 4 to get back to 0. All right, and my moment diagram. So we're done with the shear diagram. This one's pretty straightforward. Moment diagram, switch over to purple. Start at 0. Since my shear is 0, my moment is either constant or 0, okay? But there's no change in moment. So I started in 0, and that part of the function is a 0 as well. Once I get over here to the load, though, now I have a negative area. 4 times 2 is 8. Decrease by 8. Put 8 down here. Increase by 8 kilonewtons times meters moment. Okay, so for that clockwise moment, we jump back up to 0. Lastly, you go fill out the function. So constant goes to, it's supposed to be linear. Okay, close enough. All right, easy peasy. Next one. So that was number 6. Here is number 7, another easy one. So just like the one we just did previously, let's go ahead and replace that fixed support with some reactions. All right. I have the capability, the potential to develop a vertical force, but if I put one in there, it wouldn't be in static equilibrium. So By is equal to 0. Similarly, Bx is equal to 0. But when I sum moments, I need a reaction moment to balance this out. So it needs to be equal and opposite, equal to 8 kilonewtons times meters. All right. On to the fun part. B and M. And for our units, we have kilonewtons for shear force, kilonewtons times meters for bending moment. Here's my shear force. Start at 0. Nothing happens. Nothing happens. There is no shear force anywhere on this beam. So this is essentially Vx is equal to 0 for the domain of 0 going all the way to L. All right, moment. So start at 0, go on our merry way for the first 1 meter, hit the 8 kilonewton applied moment. This one is going counterclockwise. So for counterclockwise, we jump down. Okay, so we have our 8 kilonewtons times meter down here over 2 meters. I stay constant, and then I increase back up to 0 here. And that is it for that problem. Messed up my colors, didn't I? Okay, now it's purple. All right, looking good. On to problem 8. Again, we've got some reactions to solve. And let's see, I don't have any horizontal loads in the system, so I'm not going to have any horizontal reactions, but I am going to have verticals. So let's assume upward and upward, and I'll call this A sub y, I'll call that B sub y, and we get to do our reactions. Now remember, for the purpose of doing reactions, go ahead and turn this line load into a resultant force, concentrated load, whatever you want to call it. So I'll just put it right about there. That looks about right. Just kind of throwing it in temporarily just so I can do my moment summation. And that's my resultant force, 1 kip per foot times 180 feet make 180 kips. Okie doke. And I need some distance, so that would be, let's see, so it's 90 feet from both sides. So what I'm thinking is, why don't we just label it as 90 feet from B sub y. And then let's just do a quick moment about B, and we can solve for A sub y really quickly. All right, let's go ahead and do it. So summation of moments about B is equal to 0. I have my resultant force, 180 kips at a distance of 90 feet. Okay, and that has to balance out A sub y. Qualitatively, I know it's upward at a distance of 150 feet from B. Therefore, A sub y is equal to 180 times 90 equals divided by 150 equals 108. 108 kips. Okay, upward. And to get B sub y, we'll do summation of forces in the y direction equals 0. Everything going up, which is 108 kips plus B sub y equals everything pointing downwards, which is 180 kips minus 180 equals times -1. And I get B sub y equals 72 kips upward. By the way, one thing that I have noticed, one difference in the way that I use my calculator versus the way that I see students use theirs, is I often see students try to build really large expressions and then keep track of like how many parentheses to open and how many parentheses to close. And my process is a little bit different. And I'm not saying either is better than the others, but I find my little kind of break it apart into little chunks has resulted in me being able to do calculator operations more accurately without errors. So you may want to consider changing your strategy if you feel like that's a good idea. All right, so we've got 108 over here. 108 and 72. And I can cut all this out of it. All right. Let's see. Okay. Now that we're about to start shear and moment diagrams, get all this out of the way. So remember, equivalent forces, simplified equivalent systems, super useful for reactions, cannot be carried through for shear and moment diagrams. Cannot. We have to have the true nature of the function, which is a line load. We cannot convert that into a point load, multiple point loads, any other creative way of making a statically equivalent system. We need full equivalency, not just static equivalency. All right. I'm afraid I'm going to run out of room on this. So it's probably okay. I'll bring it up just a little bit. Okay, let us do our shear diagram in kips and our moment diagram in kips times feet. And let's see, I've been doing blue for shear diagrams. I'll continue with that. Start at 0. Now I go downwards 1 kip per foot times 30, right? So this area under the curve. Okay, so I decrease by 30 kips. I increase by 108. Okay, so -30 plus 108. Okay, that lands me up at 78. Now I decrease by 1 kip per foot times 150. That lands me at -72. And lastly, increase by 72 to get back to 0. What type of functions are we looking at? Well, all of this is constant, so everything down here is linear. So linear, jump up, discontinuity, and linear. Good, that was awesome. And jump up. There is my shear diagram. Time for moments, switching to purple. Start at 0. Calculator at 0. Okay, the first thing I need to do is put in a negative area of this first piece. So I'm going to say negative, open parentheses, 30 times 30 divided by 2 because it's a triangle. That gets me to minus 450. Next piece, I have a big positive area, so I want to increase. And we're going to have to figure out the base of this triangle. So we'll use our little trick. 78 kips divided by 1 kip per foot. 78 kips divided by 1 kip per foot equals 78 feet. So we have 78 feet between here and here. Similarly, we have 72 feet between here and here. So my calculator has got this negative 450. Let's add the positive area. So plus, open parentheses, 78 kips tall times 78 feet wide times 0.5 because it's a triangle, and hit enter. So we're up to 2592. 2592. Goodness. All right. So huge amount of positive moment here. 2592 kips times feet. All right. Next, we reduce. So put a minus sign, open parentheses, and the area of this triangle is 72 times 72 divided by 2. 72 times 72 divided by 2 equals. And we're back to 0. All right. Last piece is the nature of the curve. So we've got linear and linear. Linear integrates to quadratic. What type of quadratic? That's not a good color. Let's try this one. These points decrease in value, get more negative from left to right. These points decrease in value, get more negative from left to right. Therefore, bending moment is concave down. And this is going to be a nice smooth parabola. So down to here, and then the other piece comes all the way up here, catches that point, and then comes back down. Boop, boop, boop. And as a reminder for your professors to double check and make sure that you know what you're doing, please label these as quadratic or higher order functions. We'll do cubic and quartic type functions a little bit later. Right now, we're just starting with some of the basics. Okay, 2 more to go. Problem 9, a similar problem. So it's still 180 feet long. The load is 1 kip per foot. We need to get some reactions on here. And it's kind of an interesting problem because it's got a balance point right here in the middle. So that reaction is actually going to pick up 100% of the load. Maybe I'll call it A sub y. And over here at B sub y, I had some potential to pick up some force, but it's already perfectly balanced. So that reaction is actually going to be 0. That support's not doing anything. So 180 times 1, so I have 180 kips up. And now my reactions are done. We're ready for shear and moment. Do some lines. This one's so similar to the prior one that I'm going to go through this pretty quickly. In fact, I worry that this video is so long that no one's listening. So if you're listening to this, email me and I'll give you a free car. All right, let's do it. So here's my shear diagram. in kips, my moment diagram in kips times feet. Blue for shear diagram, start at 0, decrease by area under the curve. That lands me down here at 90, increase by 180, decrease by 90, back to 0. There's my shear diagram. Moment, switching to purple, start at 0. I need the area under the curve. So I've got 90 times 90 times 0.5. That gives me 4050. Okay, that's negative, so I land down here. The 4050 kip feet, if you wanted to show engineering notation there, that would also be okay by me. I'm going to try to figure out a way to put this out of the way a little bit. I'm going to put it right here. All right, and then positive by the same area, that gets me back to 0. Now I need to do the function itself. Linear, linear, make quadratic, quadratic when I do the integration to the higher order function. And decreasing values mean concave down. So concave down, concave down, boop, boop. Now remember that we talked about this earlier in the course, but haven't revisited it in a while. And we're seeing something interesting pop up here. So let's just see this real quick. We've got a symmetric loading function that integrates to an anti-symmetric shear function that integrates back to a symmetric moment diagram. So that's a pretty cool pattern. We haven't done too many symmetric ones. To go all the way back here, right? But this was symmetric, integrates to anti-symmetric, integrates to symmetric. And I think it was the same here. So symmetric to anti-symmetric to symmetric. So it's just a calculus thing, but it can help you solve these a little quicker and also, troubleshoot errors. So symmetric integrates to anti-symmetric, integrates to symmetric. So we see that on several of these examples. All right, back to this one. Number 9's done. So last problem, number 10. Woohoo! Problem number 10. Oh man, this is an annoying problem. Who made this up? I think I did. Sorry. All right, well, we got to deal with it. Sometimes life just isn't easy, but we got to get the reactions first. So let's focus on that. So I don't have any horizontal forces in the system. And now I'm going to get some verticals. So I've got A and B. And I'm gonna, looking at all these loads, goodness, my gut is telling me they're probably going to point upwards. So let's go ahead and make that assumption. And we can call them AY and B sub Y. All right, let us do some moments. All right. Oh my goodness, what a mess. All right, let's do some resultance forces actually before we do that. So I have this chunk of line load. It's a 4x2. That makes 8 right here. So I'm going to put 8 kips right there. And I have this little triangle. And it is 2 times 6, 12 divided by 2 because it's a triangle. 12 divided by 2 is 6. So my resultant force should be 6 right here. 6 kips. And while we're doing reactions, I can ignore all of this stuff. When we come back to do shear moment diagrams, I got to bring it back. Super important that you understand and realize that, okay? All right, but for now, we can take this away. All right, we have this going on, we have this going on. Let's redimension this, or let's get some useful dimensions. So I think I'm going to do my first moment about, I guess, A. We can do, sum of moments about A is equal to 0. So my 16 measures 4 feet from A. My 8 measures 4 and 2, 6 feet from A. My B sub Y measures 8 feet from A, and that's 6 kip force. That's my cat in the background, by the way. That 6 kip force measures 8 plus 1/3 of 6, so that's going to be 10 feet away. All right. I got to pause the video and put the cat outside because she's trying to sit on the laptop. Give me just a second and I will be back. All right, I'm back. The cat is outside. We were in the middle of doing our moment summation. Summation of moments about A is equal to 0. So the way I do this, even after all these years, even teaching this so long, I'm left-handed, so I write out the calc with my left hand. My right finger, I kind of keep it on point A, so I can remember about what axis I'm actually doing my moment summation, and that helps me make less errors. I'm also kind of scanning ahead, and because I have these equal and opposite moments, one of them is going to be positive, the other one is going to be negative, so I'm just going to exclude both of them because I know they're going to counteract each other. Okay, let's go ahead and do it. So first term, so I've got 10 kips at a distance of 2 feet. That one is positive about A. I have 16 kips at a distance of 4 feet. That one produces a negative moment about A. I have 8 kips at a distance of 6 feet. That one produces a negative moment about A. I have 6 kips at a distance of 10 feet. That one produces a negative moment about A. And I have my unknown B sub Y at a distance of 8 feet. That one produces a positive moment about A, and all of that is equal to 0. Again, when you write out these calcs, tell your audience, whoever is reviewing or checking your calc, tell them what you're doing, like what is the operation, make sure they know what your summing moment's about, then execute it and make sure you set it equal to 0. That's the best way to do these. All right, I'm going to spot check my signs, make sure I haven't made a mistake before I start punching this through. Negative, negative, negative. Yeah, it looks good. So let's punch it through. So 10 times 2 minus 16 times 4 minus 8 times 6 minus 6 times 10, okay, times negative 1 divided by 8. And that means by is equal to 19 kips. And I'm just going to, anything with that many steps, I usually do it twice, just to make sure. Yeah, if I get the same answer twice, that means it's probably good to go. Okay. Especially in these shear moment diagrams, right? Because if I mess up this calculator operation and I just run with this, I'm not going to discover that my answer is wrong most likely till I finish the moment diagram. And if I don't end at 0, it's probably because I messed up my reactions. All right, we've got B sub y, summation of forces in the y direction equals 0, upward is positive, so minus 10 kips plus A sub y minus 16 kips minus 8 kips minus 6 kips plus 19 kips is equal to 0, negative 10 minus 16 minus 8 minus 6 plus 19 equals times -1 equals a sub y is equal to 21 kips. All right. Let us get that information on the drawing. So here's what I'm going to do. I'm going to remove all of this. Okay, fantastic. My original function comes back. I'm going to need that in the next step. I will remove this and this and replace with by of 19 upwards, ay of 21 upwards. And now that I've got that, I will also clear all this out. And again, I'm doing all this right because this is a solution video. I'm not suggesting that you should delete your work or erase your work. You should definitely include all of your work. But for this particular video, once I've got those reactions done, I don't need any of that stuff again. All right, I'm going to have a lot of lines on this one. Okey-doke. I'm going to put my shear up just a bit, I think. Shear, units of kips, moment units of kips times feet. Shear, blue marker. Let's do this. Okay, so I start at 0. And for the first 2 feet, nothing happens. Then I start following the direction of the arrows. So -10. 0 minus 10 equals. Okay, great. So I'm down to 10. And nothing happens. Then I add 21. Nothing happens. Remember, I ignore the moments while I'm doing my shear diagram. Now I drop by 16. Now I drop by 2 times 4 equals 8. Trying to draw this roughly to scale. Increase by 19. And decrease by the area under the curve. Open parentheses, 2 kips per foot high times 6 foot wide times 0.5 because it is a triangle. And sure enough, that gets me back to 0. Okay, I'm going to go ahead and put the rest of these lines in here. Okay, so I have a 0 function, a jump, constant, a jump, a constant, a jump, a constant goes to linear. Now, jump up. And now the one we need to figure out. So we have a linear that integrates to quadratic, but is it concave up or is it concave down? My values decrease. Oh, goodness. This is the one I got to watch. Oh, my goodness. All right. In mathematics, When we're looking at functions, we are plotting data without these arrowheads. And once we have the arrowheads, we are able to make the same picture look positive or negative just by changing the orientation of the arrowheads. So careful, careful. When you go to integrate a higher order, a linear or higher order loading function, okay, you cannot go on autopilot and say values are decreasing concave down. I almost made a huge, huge mistake. Okay, so two ways to think about this. Number one, use the principle of transmissibility. If I were to redraw these so that the arrows hung below and that the 0 point was at the 0 line, then I could go on autopilot and say values are increasing from left to right, therefore concave up. That's method one. The other way to do this is just to use principles from calculus directly. So I need a slope of 0 over here. So I'll kind of dash that in, it's kind of a slope of 0. And over at the support, I have a downward slope. Okay, so something like this. And I've got half as much slope halfway across, so something like that. And if you added a few more, you will be able to see that this is a concave upward quadratic curve. Very, 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 very easy to mix that up, but this is the one that's correct. Quadratic, concave up. Okay. Shear diagram looks fantastic, if I do say so myself. And we are ready to go to the moment diagram. Zero out my calculator for more parties. Okay. Remember my little trick about not forgetting the moments? So I have 1, 2 applied moments. They're going to make jumps in my moment diagram. So just going to do a little airbrush right there and there. And that'll be my mental note to not forget those 8 kip foot jumps up and down when we come to them. Let's go ahead and do this last one. So we start at 0. And my 8 kip foot, okay, my 8 kip foot applied moment is counterclockwise. We jump down. Okay, so -8, jump down and come down here to, goodness, thinking ahead and thinking about scale. I think this is going to be small relative to what we have to do coming up. Okie doke. Over the next 2 feet, no change. And now we have a negative area. So back to the calculator, I go minus, open parentheses, 10 times 2. Okay, so 10 kips times 2 feet. That lands me at -28. That is not correct. Sorry about that. Here is where -28 is. That's where -28 is. How do I get there? Constant integrates to linear, so I'll add that in as well. Okay, next chunk. Over the next 2 feet, I increase by 11 times 2. So plus 11 times 2 lands me at -6. How do I get there? Constant goes to linear. And I am remembering to jump, but I'm looking and I noticed I put the airbrush in the completely wrong location. I bet you noticed that right away. Goodness, there's not going to be an easy way for me to fix that. Sorry about that. That was just a goof on my part. Okay. Making mistakes is okay. All right, we got to jump by the 8 kip feet, and it is a clockwise one. Clockwise means jump up plus 8. That lands me at positive 2. Now, another positive chunk. 2 times 11 is 22 plus 22. Add that in. Now I'm at 24. Constant integrates to linear because the derivative of a linear function is a constant slope. And now we got a trapezoid. It's going to be negative. Okay, so I need that area. So minus, open parentheses. And I'm going to take the base of 4 feet and multiply that by the average height. Okay, gets me down to negative 12. Last piece, I've got this quadratic area under the curve. It is positive. It is positive. So I'm going to start with the plus sign. I'm going to open parentheses. And this is the one where either you have to go back and write the equation of that quadratic function and then evaluate it between, this coordinate and this coordinate. Maybe that's x equals 0 to x equals 6, or maybe you have your origin somewhere else. Okay, you can do that, but you don't have to. Way too time consuming. What we can do instead is look at the bounding box that goes around that function. And we have a quadratic function. We have the small piece of the 2 chunks in the bounding box. So the small piece is 1/3 the area of the box. Okay, so over in my calculator, I'm going to do plus, open parentheses, and the area of the box is 6 kips, 6 kips times 6 feet, and I need 1/3 of it. So divide that by 3. And that should get me back to 0. Whew, I'm doing all these problems live, and I'm always worried I'm not going to get back to 0, but looks like I haven't made any errors today, which is awesome. If I haven't caught them yet. Let me know. All right, let's get back to 0. All right, we've got most of our curves sorted out. So we have a discontinuity, jump, linear, 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 jump, linear. Now we have a linear which needs to integrate to quadratic. Values decrease from left to right, so we can go on autopilot and say concave down. Okay, this is a pure mathematical function. That's why we can go on autopilot. This thing with the vectors, goodness, we can manipulate the arrowheads to change the meaning of that. So use caution with going on autopilot for those. In fact, don't go on autopilot for those. Last piece, quadratic integrates to cubic. So let's write in cubic. I'm going to need to label that. And my values are decreasing from left to right, so that means cubic concave down. So here's what that function is going to roughly look like. Okay, when you're drawing by hand, you can't really tell the difference between a cubic and a quadratic function. In cubic, the rate of change is more pronounced, right? So you'll get a bigger rate of change here compared to here. So I try to exaggerate that, but there's always so much you can do when you're sketching these things by hand. Sometimes I have students, once they see cubic, they start to do like crazy things. So, they're thinking of this type of thing. And so somehow this becomes, just something weird, something weird. So don't do that, right? Just interpret this really, really literally. Go back to the website and look at the flip book on, how to do this integration method if you need to do so. But the cubic function that I've got here is the one that is correct. And we are done with these diagrams, which is pretty cool. So thanks for watching the long video. I really hope it was helpful to you in getting through these shear moment diagrams. Once you got the hang of it, they're pretty fast, and hopefully the use of the calculator has given you some techniques and strategies for how to approach this work as you're solving your own problems. Thanks for tuning in, and signing off.